Beginning with linked oscillations, we will build a model of computation that is not sequential, not synchronous, has no global referent, and no central control. Modeling not so much the computations of a mathematician with pencil and paper, but more the computation of the cells in her body. Not a sequence of timed or controlled steps, but a behaving structure of flow relations. We begin with two oscillations linked through a completeness behavior. You'll notice that the completeness behavior doesn't allow red to pass until both inputs are red, and it doesn't allow blue to pass until both inputs are blue. So it has a red completeness behavior and a blue completeness behavior. And you'll notice that the fast oscillation always waits on the slow oscillation. So the slow oscillation is regulating both oscillations. You're familiar with this behavior in a different context in which a crystal oscillator regulates the oscillation of an electronic oscillator. But here we have two similar oscillations that are linked. They could be any kind of oscillation, but this discussion is about electronic oscillations. We can link many oscillations together through shared completeness behaviors. The oscillations continue to oscillate and continue to regulate each other's oscillation. And from that regulation emerges a stable flow behavior from oscillation to oscillation. If you look at the paths through the oscillations that do not contain the inverter, you will notice that a red wavefront stably flows from oscillation to oscillation through the structure, followed by a blue wavefront stably flowing through the oscillation through the structure from oscillation to oscillation. We'll call the path without the inversion the flow path, and we'll call the path with the inversion the closure path. And we'll redraw the structure of oscillations as shown below to emphasize the flow path. The redrawn oscillators behave exactly the same way, and now it's easier to see the flow paths and the closure paths. So an oscillation flow path doesn't have to be a single rail, it just has to look like a single rail to the closure path. So we're going to introduce oscillations with 3 rails in the flow path. We're going to define the red phase of the oscillation to mean data. We're going to define the blue phase of the oscillation to mean not data, and we'll call it null. We're going to specify that the data phase of the oscillation, only one rail becomes data. Only one of these rails becomes red. Now we can assign specific meanings to these rails. This can be one meaning, this can be another meaning, and this can be a different meaning. And on the data phase of the oscillation, we can assert one of these meanings. So we can transmit data through the flow path of an oscillation now. Now we generate the closure signal from the completeness of the data flow and the completeness of the null flow. So we introduce a behavior here that will detect those two completenesses. So this is a threshold 1 behavior. So when one input is data, the output will transition to data. So that will detect data completeness. Also, when all inputs are null, the output will transition to null, and that detects null completeness. So those are our two completeness relations. Exactly one rail is data, or all rails are null. So now the oscillations are oscillating between not just red and blue, but they're oscillating between data completeness and null completeness. So now that the oscillations are oscillating in terms of data completeness and null completeness, they have to be linked in terms of data completeness and null completeness. So now we have a spanning enable rank driven by the closure from the downstream oscillation, followed by a spanning completeness detection, which generates the closure for the current oscillation. So with multi-rail flow paths, we introduce 2 special kinds of oscillations. The first is the producer oscillation, which generates data patterns for the flow path, and the second is the consumer oscillation, which consumes any data patterns coming from the flow path. So here we have a multi-rail flow path through several oscillations in operation. There's a producer oscillation, produces patterns of data, and each pattern flows through the oscillations to the consumer oscillation. So the oscillations now are spontaneously flowing information from oscillation to oscillation. Multi-rail flow paths can flow together and interact. Here we have a 2-rail flow path with rails named M and N, and a 3-rail flow path with rails named A, B, and C. They're going to interact and produce a 4-rail flow path with rails named W, X, Y, and Z. Now this interaction is defined by this function table up here. And what the function table means is that when A is data and M is data, W will become data. When A is data and N is data, X will become data. And this function table is implemented by this rank of 2 gates, which determine A and M and X and W and so forth. And this is a min term. And the min term ensures that the output will not be generated unless there is one data from this flow path and one data from this flow path. So it ensures the completeness of the input before the output is generated. This is the link between the input oscillations and the output oscillation. Right? This is the output oscillation, and this is an input oscillation, and this is the other input oscillation. Here's the interacting flow paths, each with an input producer cycling through its flow path values. Multiple flow paths can interact to conditionally steer flow among the flow paths. Here we have a 2-rail flow path that's steered to one of 3 output 2-rail flow paths by a 3-rail flow path. The rails named 2mn, 2op, 2qr. So when 2mn is data, it steers A to M and B to N. When 2op is data, it steers A to O and B to P. Now we can do it the other way also. We can select from multiple paths into a single path, and that's illustrated here. And now we have from MN, from OP, and from QR, and this is the table that defines that behavior. So when it's from MN, M is steered to A and N is steered to B, and there is no transition activity on OP or QR. From OP, O is steered to A and P is steered to B, and there's no transition activity on MN or QR. We can close a flow path to make a ring. In this case, a 3-rail flow path is closed to make a ring. A data wavefront initialized in this ring will flow around the ring forever without changing. This illustrates a constant wavefront flowing around the closed ring. The middle rail is set in the wavefront, and the wavefront will flow forever with the middle rails set. We can link another oscillation into the ring and provide an output for the ring and also regulate the flow of the ring. So the constant flowing around here, for instance, will wait here until this oscillation requests the data, enables the data. And when it's enabled, the data will flow out of the ring, and it will also flow back around the ring. And when the null wavefront flows out, the data wavefront will flow to here, and it will sit here and wait until this becomes data again and requests the data. Then the data will, for the next data wavefront, will flow out back around the ring and wait here until this oscillation requests the data flow again. Now in the ring, we can also put a function. This is a very simple function. It just changes the rails in the middle of the ring, so that when we have E0, it goes around and it becomes E1. E1 goes around and becomes E2, and E2 becomes E3, and E3 becomes E0 again. So this is a sequencer, and it sequences between rails E0, E1, E2, and E3, and this is the linked oscillation that receives the output. So every time this oscillation oscillates data, it gets the next rail in sequence. We're going to raise the abstraction level a bit by introducing a symbol that can represent a link for any arbitrary flow path. For instance, a flow path with 4 dual rails, or a flow path with 2 quaternary rails, or a heterogeneous flow path with a quaternary rail and 2 dual rails. It also allows us to represent a function inside the symbol across the flow path. And in this case, this ring is going to flow a number around it, and each time the number flows around, we're going to add 1. So the output oscillation here will be getting a count. Here's a ring that's going to generate a random number. This this does the multiply, this does the add, this does the mod, and the seed flows around the ring, and the output oscillation will receive a sequence of random numbers. Here we have 2 linked rings. This ring is going to remember the previous value, and this ring is going to remember the previous value. And those two added are going to flow to the output. So this output oscillation is going to receive the Fibonacci sequence. We can link an input oscillation into the ring, and the ring becomes an update function. In this case, we have an add, and this is the input oscillation that delivers a sequence of numbers which are added. What they're added to is the previous sum flowing around the ring. So what the output oscillation sees is a running accumulation of the numbers from the input oscillation. The function in the ring can be a state machine. The input can be a condition. The output is the state, and the thing flowing around the ring is the current state. So the current state plus the condition determines the next state. So the output oscillation sees the sequence of next states. We can add another input to a ring, which is a command input, and create a read-write memory. So we have the ring here, and a data wavefront is stored in this oscillation, and it sits here and waits for a read command or a write command. On a read command, the data wavefront will flow through the output oscillation around the ring and back into the store oscillation. On a write command, the wavefront stored here will be directed to the sink, and the input data wavefront will flow into the ring and stop here and be stored, waiting for the next command. We can take memory rings, stack them up on a bus, enable each one with a unique address, and we can make an arbitrarily large single-ported memory. And it's just as feasible in the abstract as an arbitrarily long paper tape is. Rings can be linked together to form more complex functionality. In this case, we have our four-state sequencer coupled into the accumulator, such that only every fourth accumulation does the output oscillation oscillate. So for every 4 input oscillations, there's 1 output oscillation. So here we have 2 linked oscillations implementing an iterative function. One of the oscillations is the data flow path, and the other oscillation is a control flow path. And this function is going to do the greatest common divisor. And we're going to get 2 inputs, and we're going to do the mod, and if it's not equal to 0, then we will flow the 2 inputs around the ring again and redo the mod. If it's not equal to 0, we will flow them around the ring again and redo the mod. When it is equal to 0, then the appropriate value will be steered out as GCD and the other value sunk. Now the control here is flowing around its own ring and controlling the inputs. So when the mod is false, equals 0 is false, then this will allow the ring input, feedback input. When it's true and we output the result, then this will go back and allow a new input to be resolved. Here we have a symbol game played with 2 hands of symbols. Each hand plays 1 symbol at a time to some criterion of winning. The symbols are dealt into the hands alternately by a state machine here, which gets the symbols from a database of symbols. The symbols are randomly generated from the database by a random number generator, which addresses the symbols. Now, if the random number addresses a symbol that is already dealt, then this database will search for a symbol that's not dealt yet. When all the symbols are dealt, the database will reconstitute itself and start dealing symbols again. So here's the last symbol. Can't find a symbol. The database is reconstituting and it starts dealing again. So here we have a behaving structure of flow relations entirely in terms of linked oscillations performing a non-trivial computation.